We're very close to confidence intervals. Here is the mean heap with about 300 sample means, samples each of size n equals 20. Now those sample means are clustered around the population mean mu, and I can put on the sampling distribution curve this normal distribution here and the standard error lines. Now my question is, let's think about estimation error. Each of these means, and remember as a researcher we only have a single mean usually, each of these means we can use as an estimate of mu. Now how close are they to mu? Well, more particularly, what's the interval here that includes 95% of these sample means? Well, we know about normal distributions. If we go within about -2 standard deviations up to +2 standard deviations, we capture about 95% of the data points in this normal distribution. More particularly 1.96. If I turn on these margin of error lines, MOE lines, M-O-E, MOE lines here, that are positioned at 1.96 standard errors below and above mu, then between these lines 95% of these sample means will in the long run fall, or if you like 95% of the area under this theoretical sampling distribution will lie between these lines. And only for 5% in the long run of the sample means will we have a bigger estimation error than this MOE, this distance here. And they'll be the 5% of means that happen to fall way out in the tails, further than MOE from mu. But as a researcher, I don't know mu. I don't know the population. And all I have is a single sample. There it is, with its mean. Now I'm going to put an interval on that single mean, which extends MOE either side of that sample mean. Where is mu likely to be? Well, in 95% of cases, the sample mean falls within MOE of mu. So if I put this line MOE below and above our sample mean, then in 95% of cases, this interval will capture mu. What are we going to call this interval? Yes, the trumpets are sounding for the arrival of 95% confidence intervals. Indeed, you are right. This is the 95% confidence interval. And if we take a whole series of samples and we place plus and minus MOE on each of the sample means, then we get the dance of the confidence intervals. Yes, it's the dance of the confidence intervals. It's a representation of the extent of sampling variability as we take a succession of independent random samples, each of size n equals 20, and for each we calculate a confidence interval, plus and minus MOE, the sample mean plus or minus MOE, and we expect in 95% of cases in the long run that these intervals will capture or include mu, the unknown population mean. Now notice we're doing something very unusual here inside the computer. We're taking lots and lots of samples, running lots of experiments. Usually a researcher has only one. Now I can mark in, because I'm in the computer, I actually know where the population mean is. I could even show you the population. There it is. And I can mark capture of mu. ESCI displays in red those sample means that are out in the tails of the mean heap, sufficiently far from mu that the plus and minus MOE, the confidence interval, does not capture mu. And in the long run, we'd expect 5% of these confidence intervals not to capture mu. And as we run the dance of the confidence intervals, if we keep running for a long time, we'll find that 95% of these intervals will indeed capture mu. And down here, well, in this run, we're up at 94% at the moment after taking 226 samples. And if we leave this running for 5 minutes or 20 minutes or overnight, this percentage capture will eventually settle down to being very close to, extremely close to 95%. In the short run, we can see lumps in the randomness. There might be, no red for quite a while, and then we might have a clump. Then we might have alternating red left and right. There's one red. Another one. And here we are, 94.8, 94.9 as it happens. Now, there's no memory in this sequence. This approaches 95% simply because any early fluctuations, in our case we were down about 92% at one stage, they just get averaged out in the long run. Oh, look, a whole screen with not a single red. Oh, is that really random? Well, randomness is endlessly surprising. The short term, we get a bit of a clump. Several red altogether. But in the long term, take a very long sequence, then we get very, very close indeed to 95.0. In fact, right now we're sitting on 95.1. So that's the dance of the confidence intervals. Enjoy. Now, what would happen if we took larger or smaller samples? Let's take much larger samples, say n of 80, that's 4 times the size. We would expect, of course, we get many more points, 80 points in each sample. We would expect the dance of the means to be much tighter. We would expect the sampling distribution of the sample means to be much narrower, standard error to be smaller, just half, because n is 4 times as large. And so all these confidence intervals would be shorter because we've got more precise estimation. But still they're 95% intervals, so in the long run we expect just 5% of them to be red and 95% of them to capture mu. And here we are on 93.6. We got a big bunch there, that dropped the percentage a bit. Down to 93.2, and if we leave this running for a few minutes, we'll get very, very close to 95.0. And you could try this, of course, with a much smaller n or an even larger n, and you'd correspondingly get longer or shorter confidence intervals. But if they're all 95% intervals, you would get 5% red. I've gone back to n equals 20, and I'm now looking at the dance of the confidence intervals there for n equals 20. 100% capturing so far. That can't be random, really. Well, run it for long enough and it will be. Short-term lumps, long-term absolutely predictable. Now, I've been talking about 95% confidence intervals. Suppose we wanted 99%. Suppose we wanted confidence intervals that were more likely to capture mu. Would we need longer intervals or shorter intervals? You probably figured out we'd need longer. And if I change this spinner here to go up from a confidence level of 95 up to 99, all the intervals get longer. And in fact, some of the red, or the 2 red we saw there, now become green because they capture. Let's start again with 99% confidence intervals, and we would expect just 1% of intervals to be red. So we might have to wait for a while before we got very many, but in the longer term, we'd expect this percentage capture to settle down to 99. And of course, if we change down to, say, 90% or even 80% intervals, then the intervals would be distinctly shorter and many more of them would be red. In fact, in the long term, we'd expect 20% of them to be red and 80% to capture. Here we're sitting on 81%, 82%, 78% capturing